Hello everyone. Today we are going to continue how to find the number of outcomes in a given probability problem. So as we started yesterday, we started counting outcomes by using tree diagrams, but we can find the total outcomes in two ways, not just with tree diagrams, but using this principle called the fundamental counting principle. And we're going to learn how to use that as well as a tree diagram to count a total number of outcomes. So remember, tree diagrams and the fundamental counting principle are two different methods to find the sample space of a probability problem. However, sometimes tree diagrams work better for some problems, and the fundamental counting principle works better for other problems. So let's look at an example of that. So let's say we're asked to find the number of outcomes here. Andy has 6 shirts, 8 pairs of pants, 12 pairs of socks, and 7 pairs of shoes. We're going to sketch the diagram to determine how many different outfits Andy can choose to wear if he picks 1 shirt, 1 pair of pants, 1 pair of socks, and 1 pair of shoes. So if I were to go ahead and draw this, I would have to start my tree diagram with the first choice, which is him making the choice of his shirts. So I would say shirt 1, shirt 2, shirt 3, shirt 4, 5, and 6. Now we have 8 pairs of pants. So each of these options for the shirt would need to have 8 branches on it. And you can see at this point, 2, 3, 4, 5, 6, 7, 8, we see that we have a lot of options. So this tree diagram is going to become very, very massive once I put all these branches just for the second level. It's going to become a very massive looking tree. And then I still have to write down pant 1, pant 2, pant 3, pant 4, 5, 6, 7, and 8. And then from each of these little branches that I just drew, I would have to draw 12 more branches to do the socks. So off of each of these right here, I would have to draw 12 more little branches here. And then off of this one, 12 more. Off of this one, 12 more, and so on, right? So again, as you can already see, this tree is going to become very, very, very complex. And once I have that part, I just have to write down 7 more branches off of each of these guys right here. So I'd have to do 7 more. And I have to do it a whole bunch of times. So I'm going to get this great, ginormous tree. So drawing this tree diagram would not be very efficient here. It would take forever. It's possible. It'd probably take up a lot of space and a lot of time. So here we would not want to do a tree diagram. This is where the fundamental counting principle becomes useful because it's a faster way of doing this. Some of you guys may have already noticed that there is a kind of a shortcut to this, because once you add the same number of branches to each prior branch, it's adding the same amount to each branch, which is repeated addition, and that is just a shortcut way of doing, a longer way of doing something we shortcutted, which is multiplication. So we're going to go ahead and use multiplication for the fundamental counting principle, because it's just multiplying the number of branches that are being added to the next level. So the basic idea of the fundamental counting principle is, or the basic counting principle is the following. It can be used to find the number of possibilities, so the total outcomes, when given several groups. So several groups, we mean several choices or options to make our next choice. So again, it's a quick way to find this without doing the tree diagram. It's just an alternate method. Now the question is, how do we do that? Main thing is we're going to be multiplying. So you multiply repeatedly in this case the number of ways each event in the experiment occurs. So how many choices do we have for the first event? How many choices do we have for the second event? And so on. So again, bullet point 1 says multiply the number of possibilities for the first characteristic or the first event times, multiply, to the number of possibilities in the second. So we do the how many choices we have in the first event times the number of choices in the second event. And if there are more than 2 outcomes, we keep multiplying the next set of possibilities. So it's all just multiply the first amount by the second amount by the third amount, and we keep going if there are more. So let's go ahead and see an example of that in action where we're not drawing the tree diagram. So it says, how many different California license plates are there altogether? So California license plates begin with a number. It's followed by 3 letters, and after that there are 3 more numbers behind that. So it's number, letter, 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 number, number, number. So we're going to go ahead and look at those choices. So again, I have to multiply 7 options because I'm making 7 choices, 1 for each character in the license plate. So one way I like seeing it is like I'll just put a line for each option. So 1 option, 2, 3, 4, 5, 6, and 7. So here's my license plate. There's 7 spots to be filled. And between all the options or the characteristics here, I am going to multiply the numbers. So you're going to get a very big number here. So if my first character is a number, I have to ask myself, how many numbers are there in the number system? We have 10. 1 through 9 plus 0 gives me 10 numbers. So there's 10 different numbers that can go in the first spot. So if I were doing a tree diagram, I would put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 across, and then start branching from there. Now, the next 3 are letters. So how many letters do we have in the alphabet? We have 26. So A through Z, we have 26 letters. So that means these next 3 spots, we have 26 choices of the letter that we can fill these spots with, whether it's A or K or J. There are 26 spots that we can fill here with different letters, 26 more spots that can be there, and in this third spot as well. Now the last 3 spots are filled with numbers again. So we're going to go ahead and put 10, 10, and 10 for all 3 of these as well. And then we're just going to go ahead and multiply this number. And we end up getting this really, really big number, of course, which is 175,760 with 3 zeros. So we get about 175,760,000 license plates. That is how it's possible that no 2 people end up with the same license plate, because there are so many options that we can use using this 7-digit combination. All right, let's go ahead and move on to the next one. All right, we have, if a lottery game is made up of 3-digit numbers from 0 to 9, how many number combinations are there? So here we have 3 choices for the first digit, the second digit, and the third digit. And the possibilities are from 0 to 9. So we have the number 0 to 9, so that means there's 10 choices. So we're going to go ahead and fill in each of those spots with 10. So 10 times 10 times 10, and that's just going to be 1,000. So 3 zeros. So there's 1,000 different combinations that we can make with a 3-digit number. We're using all numbers from 0 to 9. Let's look at number 3. This summer you are planning to take 3 courses at a community college: geometry, English, and chemistry. There are 8 sections of geometry, meaning 8 different classes of geometry, 5 of English, and 4 of chemistry. Assuming no scheduling conflicts, how many different 3-course schedules are possible? So we're going to be making 3 choices: our choice for our geometry class, our choice for our English class, and our choice for our chemistry class. So for our geometry class, I'll put a little G down here. We have a total of 8 sections, and there are 8 choices to make, so we can pick one of 8 classes. English, we have 5 choices we can make from, 5 different choices, and for chemistry, we have 4 different courses we can pick from. So we have 8 choices, 5 choices, and 4 choices. We go ahead and multiply. 8 times 5 is 40, and 40 times 4 is 160. So that tells me that there are 160 different ways that I can pick my classes, or 3 classes when there are this many options. Let's look at number 4. How many 5-digit numbers can be made up using the numbers 0 through 9? The only condition here is we cannot repeat. So we still have the 5. It's similar to number 2, but instead of 3, it's 5. And the only other condition is that we cannot repeat numbers. So you cannot have 2 1s in this combination, or 2 7s, or 3 7s, or whatever. So for the first choice, we have 10 numbers. So from 0 to 9, there are 10 numbers. We've already established that a few times. Now, for the second choice, since we've already used a number in the first option, there are now 9 numbers to choose from. So for example, if my first number in the combination were 7, the next number in the combination none of the next numbers in the combination can be 7s. So from our 0 through 9, 7 is now out of the loop. So we now have 1 less number to choose from. So which means now we only have 9 options left. To pick the next number, we've already used 2 numbers in the first 2 spots. So from the 10 numbers we originally had, 2 are out of the options because we cannot repeat. So now we only have 8 to choose from. And then so on. We're removing one number each time because we cannot repeat. That means 7 and then 6. So this is my number of options. We get a total of 30,240. Whereas if we could repeat, we would have probably gone 10 to the 5th power, which is a way bigger number. Let's go ahead and move on to the next one. All right, so we are taking a multiple choice test that has 10 questions. So we're making 10 choices as we're answering our questions. Each of the questions has 4 answer choices with 1 correct answer per question. If you select one of these 4 choices for each question, you leave nothing blank, means you answered everything. How many ways can you answer? So we have 10 choices to make. A choice for question 1, question 2, question 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 choices to make for each question. Now, how many options do I have for question 1? So there are 4 answer choices. So I'm guessing A, B, C, or D. So I have 4 choices for the first question. Next question also has 4 choices, so all of these will be 4s. I have 4 choices to make for each question. And this is just really 4 to the 10th power. So let's go ahead and figure out what 4 to the 10th power is. It's going to be a fairly large number. It's going to be 1,048,576. All right, let's go ahead and move on to the last one. So again, over a million different ways to answer this quiz, and only one way to get the answers all right. All right, telephone numbers in the U.S. begin with a 3-digit area code, followed by a 7-digit local telephone number. So again, total 10 digits. Area codes and local telephone numbers cannot have a 0 and 1 at the beginning. So how many telephone numbers are there? So remember, we have the area code, that's 3 digits. I'll put little parentheses to mock a number. Then we have our 7-digit area code. So here we have what a phone number would look like. And again, we have, options from 0 through 9. But again, the only thing is, the area code and the local number cannot begin with a 0. So we can have no 0 or 1 here and there. So you cannot have a 0 or a 1 on either of these 2 spots. So from our 10 numbers, 0 and 1 are out. That means we're only left with 8 options for the first number. The other numbers are all going to be 10. From 0 to 9, we have 10 numbers. So again, no 0 or 1, that drops by 2. Everything else is going to be a 10. And we just go ahead and multiply this. And the total number of telephone numbers would be 64. And it's going to be followed by 8 zeros. 2, 3, 4, 5, 6, 7, 8. So we have 8 zeros following the 6, 4. So you can see that there are a whole bunch of numbers, meaning over almost 6.5 billion different phone numbers you can have in a specific area code. All right, so that's pretty much the fundamental counting principle. It's just a matter of multiplying and always choosing the correct number of options for each spot. All right, go ahead and start practice, and good luck.